My name is Nathan Sturtevant. I'm a professor at the University of Alberta, and this is part 1 of 3 of a SoCS 2020 masterclass. Overall, the topics we're going to cover are about recent advances in heuristic search, and I'm going to structure it around the phrase, "You have heard it said, but I tell you." And if we look back 10 years ago at SoCS 2010, we found a paper there by Robert Holte on common misconceptions concerning heuristic search. And Rob covers a number of different algorithms, ID A*, things about heuristics, and misconceptions that are commonly held in the field. And in this talk today, I'm not just going to talk about the misconceptions, but I'm also going to use them or use some of these ideas as a launching pad for talking about some of the recent research that's gone on in the last 10 years. And first I need to define the problem that we're looking at. What is a heuristic search problem? And we're going to define that by looking at a state here. So this is a 3x2 sliding tile puzzle. We have a start state, which is this arrangement of tiles 5, 4, 3, 2, 1. And we have a goal state. We're trying to get them arranged 1, 2, 3, 4, 5 with a blank in the upper left-hand corner. And the goal of a heuristic search problem is to find a path that gets you from the start to the goal. And we have a heuristic that it gives me some guidance in terms of a distance measure of how many actions it's going to take me to get from the start to the goal, or the cost of those actions. And so we're looking for something like a sequence of actions here, taken one at a time, that will eventually transform the start state into a goal state. There we go. So just writing this out, we can see a search problem. We're given a start state, a goal state. This could also be a goal test function. It doesn't have to be an explicit goal state. It could be a successor function then that tells me how to get the successors of a particular state. A cost function, which tells me the cost of applying an action or cost of getting a successor. And altogether, these give us an implicit graph. So it's a graph that's not always explicitly represented in memory, but we can generate it through successive calls of the successor function. And then we have a heuristic function, which is allowing me to guide the search, or is giving me numerical information about the distance from the start to the goal, or from any given state to the goal. And the goal for this part is going to be to find an optimal path between the start and the goal. Now you may have heard it said that A* is optimal up to tie breaking. And so that's the first thing we're going to look at today. Now if we go back and look at the original A* paper and some of the theory in there, we'll describe what these F-costs are in a minute if you don't remember that. But A* looks at states from low F-cost to high F-cost and expands them in that order, so that when it finds the goal with a higher F-cost, it'll have already proven that no smaller F-costs exist to that state. And what this paper says is that there is a tie-breaking strategy for A* which can match the performance of other equally informed admissible algorithms. So the idea would be that that if there's some other algorithm there that beats A*, it's only going to be either because it's more informed or because it's got tie breaking, and there would be the possibility of giving A* that same tie breaking. Something I want to point out here, which will be relevant later, is this notion of being an algorithm being admissible. Admissible means that we'll find optimal solutions. And that's a different definition than admissible heuristics, so we'll come back to that. In this theory, they have an implicit graph they call G of n, and that's the graph that's rooted at some source node n, and so that's the theory is related to that implicit graph. And so this is a bonus you have heard it said. May have heard it said. This is actually posted on a popular Q&A site last week. It's impossible for breadth-first search to beat A*. And Holte 2010 again actually debunked this and said, well, no, it is possible. So I'm not going to tell you that, but you can read Rob Holte's paper. And the reason would be, well, A* has a single tie-breaking strategy, and breadth-first search is actually more informed. It knows what all the edge costs are. And when you combine these together, you can find instances where breadth-first search can beat A*. They're not common, but at least to be exactly precise, it is possible for that to happen. Okay, so if we look at a later A* theory, remember again, F-cost is the estimate of the total path length. Decter and Pearl in 1985 wrote a quite comprehensive paper that looks at this theory and really handles the theory at quite a deep level quite a deep level. And so they defined actually 4 different types of optimality. or different types of tie breaking and other things like this. And I'm not going to go into all of those, but just to point out that, yes, this is where we get this phrase, it's optimal up to tie breaking. And again, they say that A star must expand any state S or all states S with f of S less than C star, where C star is the optimal solution cost. And they, too, have a caveat, which actually, let's look at this construction first. So the construction is we have a start state, a goal state. We've done some search up to some state U. And imagine U is the next state I want to expand. So it has a G cost so far, which is the cost of the path from the start to U. We have a heuristic, which is the estimated cost of the path from U to the goal. And again, the theory says that if U is not expanded with the F cost, that's G plus H, less than C star, then if that algorithm, maybe it found on some particular instance, it found an optimal solution, but we can construct a new problem that in all ways was otherwise identical, and we simply take that H cost and we replace it with an edge of exactly cost H of U, and in that problem, the algorithm that didn't expand U would not find the optimal solution with some cost that's less than C star in the original problem. So that's the way that the proof is constructed, and it's based on this analysis of this picture here. And so if we go back to this theory, again, what we notice is that in this theory, they only allow node expansions to take place starting from the start state. And so very important in this theory, both of these theories, is they have actually disallowed bidirectional search. And so when we say A star is optimal, well, what about the question of bidirectional search? And so there's been a massive amount of progress in this area in the last few years. And so what I'd like to do here is cover some of this and provide just a primer on some of the theory and some of the work that's taken place there. Okay, so we would like a theory of what nodes are necessary to expand in bidirectional search. And that theory is quite a bit more complex, or a little bit more complex. Maybe it's a little bit unintuitive compared to A star. It takes a little bit more work to understand. And so one of the things I've done is created a game that allows you to play and understand, in the loose sense of the word game, but it allows you to play and understand what is going on when we talk about necessary expansions. Now, normally I would have my live audience try and play this game, and we would all, as an audience, try and draw some conclusions from that. But since we're doing this remotely, I'm going to have to do this. I'm not going to play the game, but I'm just going to show a video that illustrates what's going on. So we have a particular problem here. We have a start state, which is the red state, and we have a goal state, which is the blue state. We're trying to search in between. And again, if A star were to solve this problem, we could mark out all the states with F less than C star. Those would all have to be expanded. The ones with F equals C star are not necessary expansions. So the goal state in blue is not actually a necessary expansion. And one of the reasons for this is that A star will come to this state, it will take it off of its open list, but it won't actually get its successor. So it doesn't actually expand the state. It finds it on the open, and then it terminates with a solution. Okay, so what we're going to do is we're going to our job is to choose a state here that we think a bidirectional search must be required to expand. And then there's an oracle inside this demo that is going to try and find an algorithm that doesn't expand that state, a bidirectional algorithm. So we can watch this. We choose some state, and then the oracle chooses an algorithm and runs it. And we see actually the state is green, which means it was generated, but it was never expanded. Again, green is generated, never expanded. So these are states that are not expanded. And so the question is, can I find a state that must be expanded? So even the previous state, which is on the optimal path, or the goal here is on the optimal path, but the goal doesn't have to be expanded. The start state doesn't have to be expanded. We can do a reverse search. And so in general, I can actually choose any individual state in the state space. And it's always the case that we can come up with a bidirectional search algorithm that doesn't have to expand that state. And so that means that the direct theory of Decter and Pearl, talking about F less than C star, doesn't directly tell us what states have to be expanded in bidirectional search. Now we notice, however, that the only two states we can start from are the start and the goal. So you must expand the start or the goal, otherwise you wouldn't be able to get anywhere in the state space. So this is a very important property that we have. You have to expand the start or the goal, and that's actually going to get us to the theory for bidirectional search. Okay. So we make the conclusion, if you give me any single state in the world, there is a bidirectional algorithm that finds an optimal path and doesn't expand that single state. But if you give you a pair of states, that is, for instance, the start and the goal, we could avoid expanding one of them, we could avoid expanding the other one, but we can't avoid expanding both of them. So let's look at this picture then. This is the analogous picture, and we're going to do this with a front-to-end heuristic. We'll see what that is in a moment. So we're at the start state. We've done some forward search and some backward search to end up with states U and V. And then there is some connection between them. We don't know what the possible path is between them, but we actually don't have a direct way with a front-to-end heuristic of estimating the distance between U and V. What we do have is we do have an estimate of the path from U to the goal, which is our front-to-end heuristic. So we have G of F, which is the GF of U, which is the forward G cost to get to U, and then we have H of U to the goal, which is the cost for estimate of the cost from U to the goal. Okay, and so that gives us an F forward, which is the estimate of the forward cost of the solution that goes from start to U, U to V, and V to the goal. Now we can do this backwards, and we do the same thing. We have a backwards G cost of V. We have an estimate from V to the start, and this gives us an estimate of the backwards F cost. And then we can look together and we can say, well, we could just end up connecting U and V directly, and we don't know anything about the path in between them, but we might be able to connect them together, and so therefore we just get G plus G. And so there's a theorem from ICAPS in 2017 that says, look, if we look at the forward F cost, the backwards F cost, and then the sum of two G costs for U and V, then the maximum of these three terms is a lower bound on the cost of an optimal solution that goes from the start to U, U to V, and V to the goal. And so the theory says that if we want our equivalent condition that we saw for unidirectional search, we now need to say if the lower bound of a path of UV is less than C star, then we must expand either U or V, but we don't have to expand both. And if we want termination conditions, which were actually mentioned in Rob Holte's 2010 paper as well, then implicitly, if I have a solution of some cost and all pairs of states with lower bound less than that cost have been expanded, then we know we can terminate the algorithm, and we've shown that we have the optimal solution. Okay, so let's look at this visually, because there's actually a very general thing that happens here for actually many, many different cases. And so here we've got a start state in red, a goal state in blue. We could look at what are the states with F less than C star in the forward direction, those are the red ones. F less than C star in the backwards direction, the blue ones. And we want to reason about them, but we need this third condition of G plus G, and that's very hard to reason about sort of individually. We can individually reason whether they're in the red or blue sets, or maybe both, but the G is a little bit harder because that's a relationship between states in the red and the blue. So what we're going to do when we want to think about this relationship is we're going to take all the red states and we're going to put them on the left side. We're going to take all the blue states and put them on the right-hand side. And then what we're going to do is we're going to label them with their G cost. And then we're going to say is, I'm going to draw a line between the state on the left-hand side and the right-hand side if the sum of the G costs is less than C star, meaning that it is a necessarily expanded pair. Okay, the optimal solution in this case is 10.5, so we can draw all these lines through here, and it gives us this graph. It's a bipartite graph between the forward direction in red and the backwards direction in blue, and what we see is 8.5 on the left-hand side is not connected to 8.5 on the right-hand side because the sum of G cost is 17, and that's greater than C star. But every other pair of nodes that meets all three conditions, so one condition is in the nodes that are selected on the left side already meet the F condition in the forward, same thing for the F condition in the back, and then the edges tell us about the G costs. And so we're going to call this the GMX graph. There's quite a lot more reasoning we could do on this, but because of limited time today, I'm not going to go in great detail. I want to cover some other topics. But this is called the GMX graph, and the GMX graph actually tells us what work is necessary to solve a single agent problem optimally. And the minimum, so what we see here actually is that because this is each of these edges represents an OR relationship, I have to expand one or the other, then this actually is describing a vertex cover. And so the minimum vertex cover of the GMX graph is actually the minimum number of node expansions that are required to solve a particular problem. And so every search algorithm that we've been using is essentially been building a GMX graph and coming up with a vertex cover, not necessarily the minimum one, but coming up with a vertex cover that covers all the nodes that are necessarily expanded. Okay, and so now let's talk about this GMX graph in a little bit more detail. So first, let's talk about some theory variants. So the theory that I've been talking about here is for front-to-end heuristics. So it comes from Eckerle, 2017. And it makes two assumptions. So one, it assumes that the algorithm is admissible. That means it's going to find an optimal solution. And it's admissible with an admissible heuristic, which means that the heuristic only has to be admissible. It does not have to be consistent. I'm not going to actually define those terms in this portion of the talk. This will be covered in part 2. But it's basically a set of theoretical requirements here. And so notice here, though, that there's two definitions of admissible. One meaning that it's talking about the heuristic, and one is talking about the algorithm, and the context are slightly different. So we have to be very careful about those definitions. It's very easy, and I've been guilty of this myself, of interchanging these terms in ways that are not necessarily what we want to, or we don't necessarily get the meaning that we want from them. There's other versions of this theory. So in the Eckerle paper as well, there's a definition for front-to-front heuristics. So this is a case where I don't have a heuristic between to the goal, but I always have a heuristic between the two states U and V directly in between them. And then there was another paper in 2018 by Eshad Shaham that said, what if we have epsilon edge cost? So we know that there's some minimum epsilon on our edge cost. So when we're connecting together U and V, we could add some epsilon. So that case was handled in 2018. And in 2018, in the same paper, it also handled the case of a consistent heuristic. And if I have a consistent front-end heuristic, you can actually infer a front-to-front heuristic out of it, because you can use the difference by consistency to assume what the actual values are. Again, I'm not going to go directly into those details. If you can look at that paper to see more about that. But I just want to say that there's a lot of different cases here, and they've been handled in different papers. And for each of these cases, there is a different GMX graph. So it ends up, for the top case here, admissible algorithms with admissible heuristics, but looking at the subset of problems with consistent heuristics, that things are fairly easy to describe here. And we can look and understand that fairly well, and that's where a lot of work has been going into in terms of understanding. We have another paper that's appearing at ICAPS 2020 that is also looking at that case. But there's other work that's looked at these other cases, and we have to be careful because they're not always directly comparable. Now, there's something very interesting that happened. In 2017, there was an algorithm proposed called for meet in the middle. And in this paper, it was observed that if we have a zero heuristic, we could outperform the algorithm with a stronger heuristic. And in this paper from 2017, the anomaly that was found is a little bit stronger than the anomaly that exists for A* and breadth-first search. And so this was brought up, and there was some understanding that was needed for that. And there was another algorithm then in 2018, GBFHS, that avoided this anomaly. And this was more analogous to the case of the breadth-first search versus A*, where there's still some tie-breaking that could cause one algorithm or the other to beat each other, but it's the same sort of case that we saw before with A*. So in 2019, there was again some more theory that came out that said, look, we can generalize the idea that was directly developed for a single algorithm to many different algorithms. And we can give these properties of algorithms being well-behaved and reasonable, which basically says, do we expand states with f greater than C*, and other things like that. And so those are fairly simple properties, but what was shown is that was actually not using this theory. And therefore, there were states that it was expanding that were, according to the bidirectional theory, did not need to be expanded. And so if you fix this with better propagation and calculation of heuristic values and necessary expansions, you could actually fix most of the anomaly that was occurring in MM up to the same tie-breaking issues as before. Okay, so that's a very interesting side note, and it came simply because in 2017, actually, the theory for bidirectional search hadn't yet been developed. And so that theory is still being applied and still being understood. And what we see, actually, is when we look at current algorithms, that algorithms fall into families based on what amount of theory they assume. So if we look at NBS, which is a near optimal bidirectional search, it finds optimal solutions, but the number of node expansions is near optimal. And this is based on a vertex cover approximation algorithm. And what's nice about this algorithm is that it's guaranteed to be no worse than the minimum necessary expansions times a factor of 2. And therefore, there's a hard bound on the amount of work that that algorithm does. The algorithm itself, though, is, because the color here is to indicate that it's based on some assumptions that are being made about the problem. So assuming that we have an admissible algorithm running with an admissible heuristic, and we're analyzing what happens when we're looking at the subset of problems where the heuristic happens to be consistent. There's another algorithm, DBCBS, which is also based on the vertex cover, but it's trying to do it more greedily. And so that algorithm also works very well. It loses the 2 times guarantee, but it can be faster in practice. Alternately, we have other algorithms. So GBFHS has used the epsilon assumption. And just also, NBS can use that epsilon assumption, but in the original work, it wasn't directly described there. And so that what it means is that when we add these different assumptions, that we get somewhat uncomparable algorithms. So the necessary expansions for NBS is relative to whatever information is actually being used there. And then we have some older work which was not well known or well compared in the community, but BAE star back from 2013, and then some new variants, DBS and DBBS from 2020. These are directly using knowledge of consistent heuristics. And using this knowledge of consistent heuristics, they're basically doing the same thing of, all of these algorithms are actually doing the same thing of getting this theory properly applied so that we don't do the node expansions that are not required, or wanting the algorithms to be well behaved. And so what we see, if we look at all these algorithms, that there's been a huge advance in the understanding of bidirectional search. And so now when we say, you've heard it said, A star is optimal up to tie-breaking. And tie-breaking is usually the caveat that we give there. But I want to tell you, actually, the actual caveat we really want to have is it's an optimal unidirectional search algorithm up to tie-breaking. That is, we need to be thinking about the bidirectional case. And A star is not necessarily going to beat the bidirectional algorithms because the theory for A star has specifically excluded the case of bidirectional algorithms in both the early papers, the original paper and the Decter and Pearl analysis. And so there's a lot of exciting work. I think over the next few years, we're going to see even more research that is going to continue this process of building better and better algorithms. And in the cases where bidirectional search can possibly be applied, then what we're going to expect to see is that the performance will still continue to increase, or we may get algorithms that have better performance in terms of being able to get things like this 2 times bound. So this concludes part 1 of the talk, looking at A star's optimal with tie-breaking and how that relates to bidirectional search. And hopefully I will see you in part 2, where we're going to look at this A star's optimal again from a different light and see a new set of algorithms that have also really changed the way that we look at heuristic search. Thank you. My name is Nathan Sturtevant. I'm a professor at the University of Alberta, and this is part 2 of 3 on a SoCS 2020 masterclass on recent advances in heuristic search. And as I said in the first part, we're structuring this around the idea of you have heard it said, but I tell you. That is, we're going to be looking more in depth about how things have changed or misconceptions that might be had about heuristic search algorithms and their properties. And we're going to define a heuristic search problem by a start state, a goal state, and a heuristic function that estimates the number of actions or the cost of the actions that it'll take us from the start to the goal state. And what we're looking for is a sequence of actions that will take us from the start to the goal one step at a time. And so here we go. In this case, we're trying to get 1, 2, 3, 4, 5 in this order from what we had previously. And so we've reached the goal state now. Formally speaking, then a search problem is defined by a start, a goal, a successor function, and a cost function. And these taken together give us an implicit graph, which is the graph of the problem we're trying to solve. And as we saw in the first session, that this is the theory for A star is defined on this implicit graph. We also have a heuristic function, which is what we're going to look at more in the second part here. And our goal in the second part, as well as the first part, was to find an optimal path between the start and the goal. And so what we're going to look at in this session is, you have heard it said, I've seen this written in paper reviews, for instance, A star is not guided by the heuristic. It just uses the heuristic to prune. And we're going to look at that claim in a little bit more detail and see what's actually going on. So we're going to look at our definition of heuristics to get started here. A heuristic is admissible if it does not overestimate the actual cost between two states. So if I'm trying to get from A to the goal, that's my heuristic. It must be less than or equal to the cost of the actual path from the A to the goal. A consistent heuristic is a little bit tighter of a definition. So if you remember, F costs are G plus H, where G is the path so far, H is the path remaining, is the estimate of the path remaining. If the F costs are non-decreasing as we go along a path, then we have a consistent heuristic. Now that's the functional definition that's actually needed for A star to have the properties that we want it to have. And what we're going to do here is just look at where that comes from, or then how we can write this down more specifically. So if I have A and B, where B is the successor of A in a graph, I want F of A to be less than or equal to F of B. If we write out this, that's G of A plus H of A is less than or equal to G of B plus H of B. And then we can expand out the G of B term. And expanding out the G of B term gives us G of A plus C of A to B. And now what we see is we have G of A on both sides, and so we can rearrange these terms and we can eliminate the G of A. And so what we get is H of A minus H of B has to be less than or equal to the cost from A to B. If this is an undirected graph, then you can actually apply this both directions. You can just take the absolute value. And this is actually very related to the triangle inequality about, two edges of a triangle have to be longer than the third edge. And so there's many different ways of looking at this and interpreting it, but what we're just interested in, we're going to be looking at is heuristics that have this property and don't have the property. So most natural heuristics that we might come up for a problem will be consistent. Manhattan distance for a sliding tile puzzle is consistent. The gap heuristic for the pancake puzzle is also consistent. And when we get inconsistent heuristics, of course, we can just make up examples. We can build examples where we set our own heuristic values, but they can arise naturally when we're doing things like compression or abstraction, or if maybe we're mixing heuristics together. So sometimes we might have many, many different heuristics that we can use. We don't know which one is accurate, and it might be very expensive to try to combine them together or use all of them. But if we randomly use different heuristics, then we get an inconsistent heuristic. But in practice, it might actually be more informed than using a smaller subset. So there's work on all of these things that I'm not going to go into here today, but suffice it to say that inconsistent heuristics can happen. And what we saw before, so this is actually another misconception here, is that A star is an optimal. In fact, if you were listening to the last session, you would have heard me say A star is an optimal unidirectional search up to tie breaking. That's actually not entirely true. So you've heard that said. Well, I tell you, actually, it's only with a consistent heuristic. I didn't give you that caveat last time. And with an inconsistent heuristic, A star can actually do an exponential number of expansions, or expansions and re-expansions, of some set of n states within the state space. There are other algorithms called B and B prime that at most do n squared expansions of n states. And I'm not going to go into those details, but it's a fairly small modification of A star to get it down from the n 2 to the n to n squared. And there's actually a broad n squared problem in heuristic search, and we're going to look at some of it here and some of it in part 3. So IDA star might do n squared expansions of n, typically as b to the d. There's a lot more to be said there, and in fact, I have a paper in the main SoCS 2020 conference with Malte Helmer, where we're looking at exactly this case in detail. And there's some overlap with the talk here, but we're covering the part that we're not covering in this talk. A star, as I said, is 2 to the n. And weighted A star, which I'll cover again in the third part, also has this n squared problem. And so there's probably, with all this n squared, there's probably an algorithm that maybe could fix all of this. So let me demonstrate what's happening, where these problems are coming from. And this is the example problem that is giving us the exponential behavior. So in this problem, A is the start state, G is the goal state. The edges are all marked with their edge costs, and above and to the right of every node is the h cost for that node. So here's the h cost. We notice that A, the actual optimal solution is 23, so A has an optimal heuristic. But the heuristic from A to E, or sorry, when we drops from A to E, it drops down to 0 at E. The edge cost is only 11, so that's actually an inconsistent edge across A to E. And so what that means is it looks like E is a very promising edge that's going to take us straight to the goal very quickly, but we've actually been fooled by the inconsistency. Because, as I said, the optimal path goes around the outside here with edge costs of 1. And key to this example is that there's this large edge cost between E and the goal that prevents the search, once it gets to E, from going to the goal, and this large edge cost is actually what makes all the other heuristics be admissible. And so I'm going to take a bigger version of this problem, and we're going to run and watch what happens to A star here. Now I'm going to run this really, really quickly because there's an exponential number of expansions. But the thing to look at is look at the last node here, what was E in the last one. But anyway, the last node before the pink one, and watch, that node is actually being expanded every other frame of the video that we're looking at here. So we can watch these expansions. The node with 0 heuristic is expanded over and over again. And this is actually a counter. It's just counting up. If you look at the costs in the search and the F costs, we're counting up 2 to the n. We have n states, so we have to count up to 2 to the n until we actually get to the goal. And so, so here we go. We did find the optimal solution, but it took us a really long time. Now, as I said, there's these fixes. In the previous problem, there's a number of fixes we can do, and they can make that problem quite a bit easier. But here's a different problem here that has the same sort of characteristics. And in this problem, we're going to see that we can't fix things quite so easily. So the structure of this problem, the way to understand it, is that there's n states on the top and there's n states on the bottom. And what's going to happen is we're going to do one node expansion on the top, and then we're going to do essentially all the node expansions of the n states on the bottom, and we're going to repeatedly do that. We're actually going to do a growing set of the n states at the end, but asymptotically, it's still as if we're doing all of them every time. Okay, and the thing to notice about the structure of this problem, so the first path on the left, we have a g cost 1, an edge cost of 1, and then an edge cost of 6. So that's 6 of all the edge costs from the middle nodes to the A, B, C, D, E, F, lowercase f, to the capital M. The largest edge cost is between A and M. It's the cost of 6. But the heuristic there is at A is 6, where the heuristic at F is 11. So the heuristic is telling me that actually going through A looks really good, but the actual best path has the highest heuristic going through F over here. So what's going on here is that the heuristic is deceiving us. What looks like the best heuristic value is actually the worst path, and what looks like the worst heuristic value is actually the best path. So we can watch this run, again, a little bit bigger example here, just so we can get the flavor of it. But we're going to do one node at the top, and then we're going to do nodes at the bottom. The purple nodes are nodes that have been expanded multiple times, and the red nodes have only been expanded once. As I said, the yellow node is the next node to be expanded. So we're just going to do one on the top, and then we're going to do all on the bottom, one on the top, and then all the nodes on the bottom. And we continue this until we have expanded all the paths on the top, and then we find the optimal solution and terminate. But here we've done n squared work, O of n squared. Now we might think, oh, this is only a artificial example, but this is an example with inconsistent heuristics. And if we look at the left-hand side here, if we don't use this BPMX propagation, but we look at this left-hand side here, what we can actually see is that we're seeing this sort of n squared behavior. And I'll play this a second time here just so we can watch this. But on the left-hand side here, what's happening is that the search, because the heuristics are inconsistent, it's being deceived. And we sort of do one node on the sort of the top level, and then we redo a bunch of nodes on the bottom level. So we actually do see this n squared performance in practice. And in this case, we're able to fix it by doing some local propagation of heuristic values, but there's no guarantee that in general we can always fix this. So we'd like to come up with an approach that's guaranteed to fix this in general, instead of approach. I mean, BPMX works very well in practice, but it doesn't have any theoretical guarantees. And again, the important point here, going back to this example, is that this left path, the one that looks the best, the one that the heuristic tells us is the best, is actually the worst path. So we're being deceived. A star is actually being deceived here by this low H cost. And on the right-hand side, it's also being deceived. The cost looks high, but it's really the left-hand side that deceives us because it says this looks really good when it really actually isn't a good path to follow. And so we'd like to figure out a way to fix that. And the way we're going to fix the problem is what we notice actually is that we'd like to if we took any of these problems and we just used uniform cost search or Dijkstra's algorithm, and completely ignored the algorithm, ignored the heuristic values in the algorithm, then Dijkstra's algorithm on all these examples that I've shown you would actually just solve the problem directly. So this would work if the entire graph was just the little piece that we saw there. But if I, of course, go on another problem where I have a very informative heuristic, then throwing away the heuristic is actually a really bad thing to do. And so what we're going to do is we're going to propose that we could take an algorithm called breadth first IDA star. It has this idea of doing something like a breadth first search, and they use IDA star with it. We're going to merge that with uniform cost search to try and fix the problem that's going on here. So first, let me just show you, if we apply uniform cost search to this problem here, where A star did n squared expansions, what we're going to see here is we just go straight from the start to the goal, and then we're done. It's very, very simple. So, and it's because the uniform cost search is ignoring the deceptive heuristic. So what is the idea that we're going to do here? So imagine that I chose some arbitrary f cost, f of I, and if I do a uniform cost search, I could prune any states with f of n greater than f of I. So the idea is I'm going to set some f cost. I'm going to do a search. Anything with f cost greater than that, I'm going to prune out of the state space. And within the subset of states that have f of n less than or equal to f of I, then all of those states, because I'm guided by g cost, I cannot be fooled by the heuristic, and therefore I will never have to do any re-expansions. I'll do exactly however many states there are in that group. The problem, of course, is how do we choose f of I? Because if I choose it the wrong way, this could be very, very expensive. And so there's a couple possible solutions to this. One is if I just had an oracle, and my oracle could tell me C star, and if I knew what C star was, then I could just do my uniform cost search using C star as my limit. I'd prune everything greater than that. And so this would look very much like A star, except the ordering would be from low G cost to high G cost, and we'd be ignoring these larger values. Now we could do this iteratively. So we could say, well, look, because I don't know C star, I don't have an oracle, I can do a search, and then I could say, well, what is the minimum F cost that I haven't seen yet? Well, then I'll search with that one, and then we'll do the next minimum F cost. And when you do that, you'll grow your F cost sort of one step at a time until you reach C star. And that works. in the sense that it will, when we get to C star, then we'll be able to know that we had the solution, and that could be fine. But the problem is that in many state spaces, for instance, where we want to use an IDA star search, the state space may not grow exponentially. And so the overhead of that could actually be very, very expensive. And we'll see exactly why in a little bit. And so what we really want to do is that we want to do this iteratively, so that in each iteration, each f of I that I choose, we're going to cause the number of node expansions in that iteration to grow exponentially. And we get overall exponential growth by getting a constant factor over the previous iteration through each iteration. So we want to do an iteration with 1 node, with 2 nodes, with 4 nodes, with 8 nodes, with 16 nodes. And if I did that, then the last iteration would be at C star. We would do at most something like 64 or 128 nodes. And we'd be guaranteed that the cost of the previous iterations would be amortized in. Now, this may sound really familiar because this is actually what IDA star is trying to do. So IDA star does iterative deepening on f costs, but it does choose the next f cost by the minimum unexplored f value. And that works when we assume that the tree grows exponentially, and so an expectation that they do. But IDA star will fail, and fail very badly, if the iterations don't grow exponentially. So again, the solution to that is a budgeted tree search, which is a drop-in replacement for IDA star. And check out the main set of talks in the conference to see how budgeted tree search works. It's very similar to what we're talking about here. Okay. But we're going to look at a variant of that. So at a higher level, we have this algorithm called IBEX. So IBEX is iterative budgeted exponential search. And this is really a general framework for solving problems where we don't know what cost to use. And there's 2 variants of this, budgeted tree search, budgeted graph search. And I'm just going to talk about the graph search variant here. So this was published in 2019 at HCI. And the idea that we want to use here is the idea of exponential search, which is an algorithm from 1976. And what we're going to do is we have assumed that we have an array where all the elements in the array are sorted, and we want to find some element, but we don't know anything besides them being sorted. So we're trying to find some element here. Maybe we're trying to find the value 27 or 27 million. It doesn't really matter. And the question is, how could I do this efficiently? And the idea is we're going to have an operator which allows us to query a state and say, is it greater than or is it less than the value that I'm searching for? So we query this, it says it's too small. Query the next one, it's too small. And if we do this linearly, then we'll do a linear amount of work trying to find this value here. But if we start growing exponentially, we can actually do much better. So the 4th entry, 8th, 16, 32, eventually we're going to query some value that is greater than the value that we're looking for. And now what we have is a lower bound and an upper bound. The lower bound is too low, the upper bound of course is too high. And we can just do a binary search inside here. And doing that binary search will allow us then to find this element. And the running time will be log of the location of that index of the value that we're trying to find. And what we can notice is that when we're trying to do these iterations on f costs, that we're trying to find an f cost that allows us to do a certain number of node expansions, then there's a correlation here. The unbounded sorted array is really all possible f costs that we could ever use. And the value that we're looking for that's associated with an f cost is the number of node expansions that we would do with that f cost. And because the number of node expansions increases, it doesn't decrease as the f cost increases, but it's non-decreasing, then what we see is that that it's exactly corresponding to this exponential search problem. So we're going to be looking for an f cost that causes the node expansions from one iteration to the next to grow exponentially. Okay, so what we imagine here is we've got f cost 10 at the bottom, f cost infinity at top. We've got the f costs of what are being mapped on this line. So maybe 27.2 is going to cause the node expansions to grow by a factor of 2. 30.7 would cause them to grow by a factor of 8. So in particular, the number of node expansions with f equals 10 on this example might be 100, with the number of nodes with f equals 27.2 could be 200. So the node expansions don't have to correlate at all to the f values, but they just have to be sorted. And maybe with 30.7, we're going to get 800. So a key idea here is that we're not going to look to exactly grow the tree by a factor of 2, but we're going to have a window somewhere between 2 and 8 times growth. And that, of course, we could use different constants there. And then if I go below this window, I know I'm going to do less than 200 node expansions. If I go above the window, I know I'm going to do greater than 800 node expansions. And the key idea here, the most important idea, is that I only need to query, am I greater than or less than or equal to the value that I'm looking for. In this case, I'm actually looking for a whole range of values. And so if I have a budget here, the idea is, I don't really want to ever do more than 800 node expansions. So I have a budget of 800 node expansions, and I should never do more than 800 node expansions to answer the question, am I above the budget of 800 expansions? So again, let's look at this in practice. We're looking for a value here that's going to cause us to do between 200 and 800 node expansions, and we're going to start querying fcost. So fcost of 11, that's going to do less than 200 node expansions, 12, 14, 18, 26. Those are all less than 100 node expansions. When we get up here with 42, we're going to do greater than 800, but once we actually do 800 node expansions, that we know that 42 as an fcost is too high, and that's too expensive. So now we're going to do a binary search until we find an fcost that gets us right within this range that we're looking for. So like exponential search, we're going to pay a log cost for finding this value that's in the range. And the cost of it is actually related to the upper bound here. So the upper bound is 800. In this case, n of I is the range, the number of nodes that we're doing at the ith iteration, because we're trying to get n of I to double. And so 800 nodes is the maximum number of nodes that I can expand in this problem. And so I do n of I times log of f of I to find one next bound. Now in practice, I have to do this multiple times until I reach the optimal solution, which is C star. And so if I look at this, when I sum this up, what I can see is that the f of i's are bounded by C star. And as long as n of i's are growing exponentially, then the sum of those is bounded by the number of nodes that I need for the problem. And the technical definition of n can be found in some of these papers. So this is where we're going to get an overhead of log C star to get this budgeted search. Okay. So we're looking at a problem here then, and what I'm going to do is I'm going to just show how this works for budgeted graph search, and we're going to start by running it. And so we're just going to watch it running. It's doing a number of searches here, and then we're going to get to sort of an interesting point in the tree, and then we'll watch it run step by step. Okay, so here we are. In the last iteration, what we've done is we've done an F limit of 18, and so we see node E here. I apologize, the heuristics look a little bit like they're associated with a node to the right, but they're actually associated with a node to the left. So E has a heuristic value of 17. It has a G cost of 1, so that has an F cost of 18. We've done everything below that with a cost up to 18. In the previous iteration, we were trying to grow the number of nodes expanded exponentially. So we're trying to do at least 12 node expansions. And in this particular problem, so we're trying to do between 12 and 48. On this problem, we actually did 15 node expansions. So we found the number of nodes we wanted. And so we're within that window. And so now what I'm going to do is I'm going to start looking for an F limit that causes the number of node expansions to double so that we're able to amortize away these costs. And so let's watch what happens. So we had 18 as the F limit in the previous problem. Now we're going to use an F limit of 19. And the node limit is going from 15 up to 30. And because 19 is actually the smallest limit that we could use, we're going to allow it to expand as many nodes as it wants because that's just the next smallest F limit that hasn't been explored. So what we're going to do is we start searching. We have F limit of 19. We search in the tree. Notice that like G, H, I, all the way up to M are not in the open list. And why is that? Well, they have F cost that's greater than 19, so we don't even put them in the open list. They're completely ignored. And when we did this, what happened? Well, we expanded 18 nodes, but we wanted to expand 30. So that says we were actually below the budget. We didn't see this exponential growth. And so what I'm going to have to do is I'm going to have to increase the F cost, and I'm going to start increasing the F cost exponentially. So here we go. We're going to add 2 to the 0 to the previous F limit. Now the previous F limit was 19, but we actually explored 19 exhaustively. So there's no reason to continue over 19. We're actually going to go up to 20 as the base value that we're adding to, because that's the minimum F cost. We're still looking for 30 to 120 nodes now. And so we run this and see what happens. So with an F limit of 21, now we've expanded 22 nodes, but we still didn't expand 30, which is what we're looking for. And so we're going to continue this process, and what we're going to do, so 22 is too low, we're going to increase the F limit We're now adding, instead of 2 to the 0, add 2 to the 1. That takes us up to 24. And even with 24, we're going to come here, and this doesn't get us to the goal, and we still only did 25 node expansions, which isn't enough. One thing to notice here is that nodes A to K are expanded in an arbitrary order. And so although A star would always expand A first, from a uniform cost search perspective, nodes lowercase a to k, they all have a same edge cost of 1, and they can be expanded in any order, and they'll all be expanded before m is expanded. Okay, so 25 is too low. Now we're going to do one more iteration. Now we're going to use a bound of 29. And so here we go. We're going to expand with 29. And now actually what's going to happen is we do all a to m at the top, lowercase, before we get to capital M in the middle. And now we're going to go down across and actually find the solution. And so the idea here is that by putting this bound on how far we're willing to go, and then growing the number of nodes that are allowed to be expanded exponentially, then we can actually, at every step, instead of using A star and being guided by the heuristic, we can instead use a uniform cost search and be guided by the G cost. This demo of how inconsistent heuristics work and the impact that they have is available online, along with many other demos of heuristic search algorithms, so you can check those out. But let me just conclude here. So you might have heard it said that A star is not guided by the heuristic. It just uses the heuristic to prune. But I tell you, actually, A star can be fooled by the heuristic, especially when it's inconsistent. And budgeted graph search cannot be fooled by the heuristic because it does not actually use the heuristic to guide the search. It uses the heuristic only for pruning instead of using it for guiding the search. It just uses it to set a limit for what to cut off. And so A star, if we know that we have an inconsistent heuristic, then A star may not be the best approach to use. Budgeted graph search would work better, at least in terms of the worst case analysis. There's still more work to do to figure out how to practically improve the performance of budgeted graph search, how to know, for instance, when you might dynamically switch over to that from A star or some other things like that. And so we'll see in practice what comes forth in the future of how to use this approach efficiently in practice. So this is the end of part 2, and we will continue part 3 looking at weighted A star. My name is Nathan Sturtevant. I'm a professor at the University of Alberta, and this is part 3 of a SoCS 2020 masterclass on recent advances in heuristic search, structured around the phrase, "You have heard it said, but I tell you." And just to recap, the problem that we're trying to solve here is I have a start state that is a configuration, in this case a 3x2 sliding tile puzzle. So it's a configuration of that state space. I'm trying to reach a goal state, which is a different configuration. And I have a heuristic, which tells me an approximate estimate of how far I am from the start to the goal. And my goal is to then find the sequence of actions that's going to take me from the start to the goal. And in this session, we're going to be looking at a slightly different variant of this problem. So just going over this again, a start, a goal, a successor function, and a cost function, all of which define an implicit graph with a heuristic function. And in this problem, in this part 3 of this session, we're going to be talking about finding not optimal paths, but we're going to find a path and we're going to put some suboptimal requirements on them. We're also going to assume that the heuristic is admissible and consistent in this section. So those terms are defined in the previous section. So you may have heard it said that weighted A star is just a simple modification of A star. But let's look a little bit more into this history and see what is actually said about these algorithms. So we're going to look at our problem definition here. It's going to be find a solution which respects some bounding function. And we'll see that bounding function a little bit later. The bounding function might be W suboptimal, so at most 1.5 times the optimal solution. Or it could be by some constant. We're going to be within 10 of the optimal solution. And there's other definitions that you could come up with. So if we look at that definition, then we can look at algorithms like A star and we can ask some questions about them. And one question in particular that's interesting, so A star is finding optimal solutions, but let's look and actually see when A star does the expansion of the search space, does it re-expand states if it finds a shorter path to them or not? So A star, the pseudocode here, says the main core loop here is we're going to expand n, we're going to mark n as being closed, saying we've already looked at it, we've already expanded it once. We're going to take a successor operator and apply that to n to get the successors. There could be 0 successors or any number more than that. Then we're going to calculate the f cost for each successor. And each one that's not already closed, we're going to mark as open. And in particular, so remark as open any node which is smaller than the cost found previously. So A star will re-expand nodes, even if they've been found on the closed list and it finds a shorter path. It'll reopen those with a shorter path cost. Weighted A star, which was originally called HPA in 1970, she does the following. When it expands n, it marks n as closed like A star, and it applies the successor operator to n. But actually, in the original algorithm, which didn't say anything about the quality of the solutions, it discarded any nodes which were in open or closed already. So even if we found a shorter path to a node in open, we actually still discarded it. It doesn't actually open, it doesn't update the cost of a state on open. And of course, it doesn't take a node off of closed and put it back on open either. And so there's very different behavior there. Most algorithms today or implementations of weighted A star would update states on open, and whether they open or reopen nodes on closed is something we'll keep looking at. So that's important. It doesn't even update states on open. But as I said, they didn't prove anything about the properties of that algorithm, so that's why we see this discrepancy, or why they didn't necessarily need to reopen states on open. Sorry, not reopen states on open, but just update their cost. So there's a journal paper from 2009 that tries to unify a number of features about weighted A star and some of the proofs that have been done with it. And in this algorithm, they say that we are going to reopen states from the closed list, put them back on open again. And of course, we would update open if we find shorter paths. And then they analyze the case of whether you do openings or no reopenings or not. And they mention, for instance, that A star epsilon must reopen states if it wants to maintain a suboptimality bound. And more generally speaking, there's a class of algorithms called focal list algorithms. And in the next masterclass by Ronnie Stern, He's going to be talking about focal list algorithms and a lot more on suboptimal search than I am here. So that's something. Just focal list algorithms in general must re-expand states, that is, bring them from closed back onto open if we're going to maintain the bound that we want. And then there's other work that's been done, like this paper from 2016, that looked empirically, that said, well, should weighted A star expand or not re-expand? And they looked at different policies, and they proposed some different things that could be done there. So there's a nice bit of analysis that's available there. And what hadn't been done is something similar to what we see for inconsistent heuristics. So in inconsistent heuristics, we must reopen nodes for us to find optimal solutions with A star. And so in 2019, we looked at, in a paper, we looked at what happens to weighted A star if we reopen nodes. And this isn't necessarily the worst case, but we can show that it's at least n squared. So in this problem, let's look at the structure of this problem. We have a set of top nodes up here. So T0 is the start and G is the goal. And the heuristic of T0 is 4, so that's up above that node. And then the heuristic of B4 is 0. So there's top nodes and there's bottom nodes. The heuristics there go 4, 3, 2, 1, 0 going across. And the edge costs going across are 1, but the cost of the edge from the top to bottom is getting smaller and smaller. And so 3.33 from T4 to B4, but from T0 to B0 is 0.67. And then the optimal solution is actually to go all the way down to E, which has a larger heuristic than everything else, and that leads us to the goal. And so what we can do is, so here's the cost, the edge cost going down. And if we I'm going to make a slightly bigger version of this problem, we run weighted A star on it with re-expansions. And what it does actually is it does n squared re-expansions of these bottom nodes, because it's going to keep going across these paths to the bottom nodes, re-expand them before it gets down to the goal. So weighted A star here can do at least n squared re-expansions. It might actually be doing worse. And what we'd like to do is ask the question, what are the set of algorithms or set of priority functions that we could use? Like, is there anything more than weighted A star that doesn't have to do re-expansions? In order to do this, we're going to analyze possible f functions that you could have, where they're a function phi of the h cost and the g cost. And you'll see why we use h and g here in a minute. It has to do with how we plot these things. So if in this format or in this framework, we're going to represent weighted A star as 1 over w times g plus h. This could be g plus w times h. That's basically equivalent, but there's some theoretical reasons why you want to write this. The interesting thing is if you write it this way, then phi is an estimate of the optimal solution cost. So typical A star and weighted A star are representing the f cost as an estimate of the solution cost that you will find. Writing it this way means that we're estimating the optimal solution cost, because we know G might have been suboptimal. It's up to W suboptimal. So that's how we're going to write this here. And so let's look at a sample problem. We're trying to get from the start to the goal. And the start is at the bottom, the goal is at the top. And we're going to look at the same problem many times in this talk. What I'm going to do is I'm actually going to plot the open list of, in this case, it'll be A star on the right-hand side. And what we have here is we have an h-axis, which represents the h cost of a state on the open list. And we have a g-axis, which represents the g cost. And so for the states down here that are in red on the open list, what we see is they have very low g cost and they have high h cost because they're near the start state. So the start state, right, starts with a g cost of 0. These are all very low. And then what happens is that A star is equivalent to taking all the states in the state space and sweeping this blue line across the state space. So let's actually watch it as we run here. And so as we expand states, we're sweeping across to this blue line. Everything on the blue line has the same priority. And we expand them from low to high according to that line. And we solve this problem and we get a solution here. And in this case, this is the optimal solution. If we use weighted A star, then weighted A star is equivalent to using a diagonal line where the slope is related to the weight that we're using. So in this case, we're using a weight of 1.5, and we sweep it across with this different angle. And we notice here actually that the line is going up and down. That's because the weight is actually creating something like an inconsistent heuristic. And eventually we'll sweep it across here, and then we'll get to the goal. So now we have a W optimal solution. And it ends up that we had a paper in 2019 that showed some general properties. And of course, I could give a whole class on just this one piece right here. So I'm just going to give an overview. And I'm not going to try and explain all of these to you, but you do see the bounding function that is in there. We have some more work that we will be putting on archive shortly that will have some of the other contributions that are going to be in this portion of the master class. But let's look at an interpretation of what these requirements mean. So one thing that they say is the slope can't be too shallow. So here we see on the h-axis we're connecting 5, and normally we connect 5 to 10. This says we can't connect 5 on this line to 4, so that'd be too shallow of a slope. It also says we should be connecting these points from the h-axis to the g-axis according to the suboptimality bound. So if we have a bound of 2, then 5 on the x-axis should be connected to 10 on the y-axis, or an h-cost of 5 and a g-cost of 0 should be equivalent priority to a g-cost of 10 and an h-cost of 0. And the other thing is that there's a limit on how quickly this line can change. So in this case, the change is uniform across this line, but it doesn't have to be. And if we want to use a different rate of change, we're going to be limited in how we can do that. So what this tells us then is we can start to derive alternate priority functions. So weighted A star, as I said, is G over W plus H, and that's just this line here. But we can do something like XUP. So this is a convex upward parabola that's following these same things, connecting these points, but we're going to go above this line, and it looks something like this, the priority function. We can do a convex downward parabola, which looks something like this line, and then something, as I said, is going to appear in this archive paper. We can do a piecewise version of this convex downward parabola, where what we're going to do is we're going to go straight across to some dividing line, and then we're going to go straight up. And so this is a little bit simpler of a priority function here than having to take the square root and things like that. So these may seem a little bit crazy, but what they're doing is they're just saying, if we have, mathematically speaking, we have these requirements. If we come up with functions that follow those, then these are alternate functions that we can do. And so let's just watch here. Oh, sorry, before we watch them, let's just look at what's going on here in this search. So what's going on is down here at the bottom, we're saying, at the bottom of the search, if the line comes out at this angle, then we're saying you can be at most, actually you have to be optimal because the slope is 1 or minus 1. But anyway, the slope is related to 1. It's basically saying you must be finding an optimal solution. But here at the top, what we're doing is we're trying to say, look, your suboptimality can be 2w minus 1. We can actually be very aggressively suboptimal. So we can have different suboptimality in different parts of the state space. And in many state spaces, that's actually really helpful. So let's watch weighted A star. So weighted A star comes across here. It's going up and trying to solve this problem. And searches up here. And we see that the curve over here on the left-hand side is a straight line. And now we come up and find the solution. So we can do the exact same problem, except now we're going to do XDP. So we're going to use this curve. And so this curve is going to basically allow us to prioritize states that are higher a little bit earlier than we would have been able to with weighted A star. And so in this case, it allows us to get to the goal doing fewer state expansions back lower down on the curve. If we do the piecewise XDP, then we're really pushing this even further. And so what we see here is now we can push up even more aggressively towards the top of this curve, towards the goal, which is always going to be on the g-axis, which is this here. And we can clearly see we did fewer node expansions. So if we just look here on this one problem in the video, I'm not going to present more comprehensive results, but in this one problem in the video, we see A star doing 9,600 node expansions, but proving the optimal solution. Weighted A star drops that down significantly, and this is with a suboptimality bound of 1.5. It's going to do about 6,500 node expansions. The solution is 10 steps worse. XDP is about 1,000 node expansions better than weighted A star, but its solution is 1 step worse. And piecewise XDP is about 2,000 node expansions better than XDP, and the solution is, again, just slightly worse again. The really interesting thing to note here is that the bound tells us that we actually could have gotten a solution of cost 400, and our solutions are nowhere. Of course, A star is optimal, but the suboptimal algorithms were nowhere near this upper limit of the solution cost that we could have gotten. And so the problem is just to find something within the bound. So we actually could be finding solutions with much higher suboptimality, and we would still be solving the problem that we're being given here. And so we have to notice that these algorithms are not explicitly trying to do anything to balance node expansions and solution quality. They're just being asked to produce a solution that is within the bound, and they're really not able to exploit the suboptimality that they're allowed to have as well as they could. And so I think there's going to be a lot more work in the future coming on this, and also there'll be a lot more in the next masterclass talking about this in practice and other algorithms that can be used for this problem. So weighted A star is, if we, node expansions is something we have to think about. It's a relatively simple replacement of G plus H, or G plus really W times H here. But we can do something very, very simple as well. So take the exact code of A star, and if H is greater than G, then just use G plus H. And if H is less than G, then we do G plus 2W minus 1 times H. And then to make these lines actually connect together, we have to divide by W to just normalize the top equation and the bottom equation so that they meet in the middle. And so this is a very, very simple replacement to weighted A star. And our preliminary results that, as I said, we'll be uploading to arXiv show that this is a much, much better algorithm on many, many problems. So this is something very simple to try, and we're still getting W suboptimal solutions. And important thing is we never have to do re-expansions with this replacement, this piecewise function that we're using. So you may have heard it said that weighted A star is just a simple modification of A star, and in some sense it is, but there's some important issues to pay attention to, whether we're re-expanding states or not. And what we see is weighted A star is actually part of a much richer family of priority functions that are still being explored, and we still expect to see more understanding of them coming in the future. So we look forward to seeing that. And that concludes my masterclass. Thank you for coming and attending, and hopefully you've learned something here today and have something to go and try and to put into practice. So thank you, and I will, for the actual masterclass, I will be online to answer questions. You can always contact me and ask me other questions that you have as well. Thank you.